Okay. So we're talking more about graphs of functions and how they behave and what they look like and what making, again, like minor changes to things. Looked at a couple of examples, a lot of detail last week, x squared and x cubed as examples of even and odd functions, right? So what we need now, kind of moving forward, because a lot of the rest of the semester after these first couple of weeks is going to be about kind of doing really deep dives on a specific family or type of function and kind of learning everything we can about it and how they work, what we use them for, all that kind of stuff. But we're not there yet. So to be able to do the stuff that we're going to do the next couple of weeks, we need some kind of sometimes some books and stuff will call these like toolkit functions or something like that. Like we need a few that we kind of know about a little bit, so that we can do the stuff that we need to know, even though we aren't quite ready maybe for what these do and how we use them. So these are just a few sort of common function types that we want to recognize when we see them. And you know, when I look at this, for example, I want to kind of have a mental picture come to mind of, what the graph looks like, because that tells me something about its domain and range and how it behaves. So the first three, y equals x squared, y equals x cubed, those we're familiar with, right? Y equals x is just a straight line with slope 1, x squared and x cubed. We spent some time with last week. X squared looks like that. X cubed looks like this, right? And hopefully you took the time to sketch these in your notes already. The rest of these might be new, but just a real quick sketch version of them. The absolute value function looks like that. These are straight lines with a, meeting in like a sharp corner. What does the absolute value do for like a number? Takes a negative and returns the positive value. Now, what an absolute value is telling us about is distance from zero, measuring like the size of a thing, but disregarding which direction it goes. So this is y equals x, that line, only you take all the stuff that was negative and you take its absolute value, which makes it positive. So sort of set up like that. That's why we get this V-shaped graph that's opening upward. What's the domain of that? All real numbers. What about its range? 0 to infinity. And one other thing about it, that's an even function. It's got y-axis symmetry. Okay, the square root looks like that. What's the domain of a square root function? Again, if it looks like that. I mean, based on nothing else but the graph, where does it start? 0, and where does it go from there? Yeah, off to the right. Okay, now if you want to think about why it does that, what the function does, the action or the operation that function performs is to take the square root of whatever you give it, right? Okay, what kinds of things can you take the square root of? Positive numbers. 0 is okay. What happens if you try to take the square root of a negative number? Weird stuff, right? If you have a calculator sitting out, just punch in like the square root of -4 or something and see what it tells you. It gives you some kind of error message. Depending on your calculator, it might say just an error, or it might say that's undefined, or it might say something about a domain issue or a non-real answer, something along those lines. All these things mean like that doesn't work. So the domain then is the non-negative numbers. The range is also the non-negatives, because the square root of a positive number is, again, positive. The square root of 0 is 0. Square root of negative numbers is not defined in the sense that we're talking about, so we don't get any negatives back as answers either. Okay, and then real quick, the cube root looks like this. Kind of the same shape. If you put them like side by side or stack them, this one's a little bit taller than this, but basically the same thing. The big difference is where this one cuts off at 0 and has like a hard stop right at the origin. This one does not. Why would that happen? How's a cube root different than a square root? Right. A cube root, so a square root, you're breaking something into two pieces, right? That's why the thing with negatives happens the way it does, because a negative times a negative is positive again. With a cube root, we're talking about 3 now, so the way negatives are going to behave and operate is different. Based on the graph, what's the domain of that thing? Yep. Yep. And the range? Same. And it's an odd function. It's got origin symmetry. Okay. So for right now, then, we have these 6, but really it's basically 5 because the straight line is probably not going to show up all that often. But you know everything about those already anyway. Function types that the expectation is that when I see them show up graphically, I recognize what they are by the shape, basically. Or when I see them show up symbolically, like written out like this, I can kind of bring to mind what the graph looks like, right? I don't like using the word memorize, but like that's kind of what we're doing, right? We need to be familiar with these graphs, these functions, so that I can recognize them when they show up. So x squared, parabola, right? We looked at that last week. X cubed, kind of like that, right? It's like you took this in and flipped it down. The absolute value, straight lines, right? V shape, sharp corner, straight lines, but otherwise behaves kind of a lot like x squared does. Domain and range look the same. It's even straight line segments instead of the curvature though. The square root and the cube root, if you look at them, they're kind of like the square and the cube, but over on their side, right? But the square root, this one is kind of the most distinctive of all these because it's got this, sort of place where it cuts off, right? The domain and range are restricted because of how square root works. The rest of those, we don't see that show up. And then the cube root, just again like that. Now, if you go up never mind, we'll talk about that later. Okay, so we've got these things, and what we're going to be doing is making, again, minor changes to them. Like, for example, making a thing that was just x into x plus 3 now. And what we want to figure out is how that affects the graph, how it changes things, whether it changes the domain or the range or maybe both, how it affects what's going on. So when I look at something like this, I want to be able to identify two things. What type of function is this? And how is it different than the parent function? The parent function is the thing that we just looked at, right? If there's nothing else going on and the only operation that happens is the square root or the absolute value or whatever, that's the only thing, then that's this, sort of basic function type graph that we're, familiarizing ourselves with. That's the parent function. Okay, so if I look at this, how do we identify what type of function it is? The square, because that was one of the things on that list of things we just looked at, right? Yeah, that's it. So what type of function is it? It's a square function. So I'm ignoring the smaller stuff, right? The things that don't matter as much. The plus 3, I'll figure out in a minute what that plus 3 does. But the main sort of driving force in what's going on in this function is the square. That's the thing that's going to determine, do most of the lifting and determining what this thing looks like, how it behaves, etc. The plus 3 part, I know how to add 3 to things. I'll figure out what that means in a minute, right? Okay, so what type of function is this? It's a square function. What does that tell me about it? That it behaves like a square function. Okay, what does x squared look like? Parabola, like that. Okay, so the function type or the parent function is x squared, which means this thing looks something like, that's the worst parabola I've drawn in my entire life. Looks something like that. And then I start unpacking all the stuff I know about that. What's its domain? All real numbers. Okay, this is defined everywhere. The kind of stuff that we're doing here is going to change that in like a small way. It's going to like move it around, right? Or shift the graph from place to place. That's probably not going to change the domain then. What's its range? Starts somewhere. It's got a lowest point, right? Look at the shape of the thing. It has a lowest point. So 0 to infinity. Now, maybe if I move things around, maybe that changes, right? Because it had a lowest point. If I change what that lowest point is, that changes the range. Doesn't change the domain though, because that was everything. Take everything, you slide it over a little bit, it's still everything, right? Okay, now how is it different than the parent function? The plus 3. Plus 3. And where does the plus 3 happen? Think order of operation stuff. Does it happen before you square or after? Before. How do we know it's before? Because it's in a set of parentheses. And order of operation says what happens first? Parentheses and then other stuff, right? Or whatever kind of, grouping acronym thing, please excuse somebody from something, whatever it is. However you keep track of order of operations, the point of parentheses, brackets, grouping symbols is to say, do this first, right? So if I gave you an x value, I said, hey, find what happens for this function when x is 5. You would take 5 and you would first add 3 to it, and then you would square that, right? Okay. So plus 3 inside that set of parentheses, meaning it happens before squaring. Okay, so it's a square function, so it looks like this. But there's a plus 3 that happens on the inside, grouped in with the variable before I square it. Now you guys, that and the other, 5 or whatever there in that first example, look at how that affects things. Right, so, if you're not sure, then actually graph it, grab a calculator or Desmos, actually graph the thing, see how it compares to the original, the unchanged, the parent function. Should be, a fairly like, easy to describe change, and then do the same thing for the other 5 that are there. Okay. We'll reconvene in a few minutes. ours, so world class. So for that first one, we're looking at x squared, but a plus 3, again, grouped in with the variable on the inside of that set of parentheses before the square happens. These all mean the same thing. What does that do to the graph? Moves it to the left 3. Let's take a look. There's x squared. Here's x plus 3 squared. Colors are hard to tell maybe. So that's the original function, the dashed one. This is the actual function that we're looking at, x plus 3 squared. So if we're looking for how they're different, same shape, but pick a point to focus on, right? Something that's visually distinct from other things on the graph. Here, right? The bottom of the parabola. That point's called the vertex. We'll talk about that later. Right now, that point looks different than all the others. It's harder to keep track of like this, because this one looks a lot like that one, right? But that one stands out. It used to be at 0, 0. Where is it now? -3, 0. Okay, well, that moved 3 to the left. So did everything else. Again, the rest of the points on the thing are a little bit harder to keep track of visually because they don't look quite as distinct, but that one does for sure. If it moved 3 to the left and we preserved the shape otherwise, then everything else did as well. Okay, so the transformation, this shifted 3 to the left. Does that change the domain? What was the domain to begin with? Everything, right? Okay, so if I flatten this thing out on the x-axis, it covers the whole thing, right? If I take the whole x-axis, negative infinity to infinity, and shift it over to the left 3, it's still. Okay, so the domain is the same. Did it change the range? Okay, those are the options. Range, we want y values, right? So we're looking for, if there's a lowest point, if there's a highest point. Is there a lowest point on the graph? Sure. Where is it? Yeah, it occurs when x is -3, but the y value, if we're talking range, is still 0, right? And then from there it goes up. Okay, so the range is still 0 to infinity then? Okay, so domain's the same, range is the same, but it's shifted to the left 3. All right. Y'all tell me about B. How's B different? The +3 is happening outside of any kind of grouping symbol. It's an order of operations thing. Here, if I give you something to plug in, what do you do with it first? First, you square, because that's the main sort of action or operation of the function, right? The thing the function does is square. So first you do that, and then you. So this +3 is happening, outside or after. And how does that affect the function? Now it's moved up 3, right? Okay, think about the function thing, right? Take x's, do whatever it does, return y's. Now what I'm doing is taking those and just making them all 3 bigger than they were. Okay, so they sit up 3 higher then, because that's what a larger y value is going to do. So we take the whole graph, again, focus on a point you can focus on, like that one. It was at 0, 0 before, now where is it? 0, 3. Okay, so it sits up 3 higher. So does everything else. But again, that's the one that's easier to spot. It was at 0, 0. Now it's at 0, 3. The whole thing sits 3 higher than it did before. So I'm going to describe that by saying that it's shifted up 3. Did that change the domain? If I flatten it out and squash it down onto the x-axis, I still get this end pointing to the left and that end pointing to the right. It's still all real numbers for the domain. Did it change the range? Yeah. The range, our lowest point was at 0 and going up from there, but then we took the whole thing and slid it up 3. So what's the lowest point now? 3. Okay, so what's the range? 3 to infinity. Good. Great. Now, I mean, I know I didn't ask you for domain and range here, but these are always things that we want to be kind of thinking about, right? Okay. Everybody feel good about stuff so far? Do you have anyone have any questions? Were you able to finish all 6 of those, or did I cut in too early? All right, take another couple minutes and just think through the rest of these real quick. I did. That's you. Oh, I know, yes. No, it wasn't, but yeah, no, I was struck very, and I could feel it coming at the end of the thing. I was like, oh, there's no way to like pause the settings or next question. Obviously. Yeah.
Okay. So, what kind of function are we looking at? Square root, right? If I ignore this kind of stuff, what's left? The square root. Okay, so square root function, what's the square root function look like? Like that, yes. That is the appropriate sound effect. Thank you, Carly. Pew! Right, starts at the origin and just sort of, curves upward and to the right, like pew. That's the square root function. Okay, lives in quadrant 1, domain and range both, 0 to infinity, 0 is included because the square root of 0 is 0. Like that. Okay. What have we done to it? Added 2. Added 2 where? After or outside of the radical, right? It's the square root of x. And by the way, like stuff under a square root or a cube root or in the top or bottom of a fraction or whatever, that all acts like it's in parentheses, whether we write them or not. Those act like grouping symbols as well. So plus 2 on the outside or afterwards. What's that going to do to the function? Shifts it up 2. Yeah, good. Everybody feel okay about that? Okay. We'll pick it up a little bit then. D kind of function. Square root again. How's it different? Plus 2 on the inside. And what does that do to the graph? Shifts left 2. And we'll talk about that in a second if the left-right thing is bothering you, because it probably should be. Okay, and then E and F. What kind of function? Absolute value. What's absolute value look like? B, right? Straight line, sharp corner. I don't know what the sound effect is for that one. Carly, if you could work on that, that would be great. You can be our official sound effect person, I guess. Absolute value. -5 on the inside of the absolute value. All right, again, that acts like a grouping symbol as well. So what does that do to change it? Shifts to the right. Okay, and then the last one, again, absolute value. -5 on the outside or after you take the absolute value, and that shifts everything down. Okay. Does everybody feel okay about those? Any of those that we want to, take a closer look at, talk about some more? Can you see, I didn't ask you for domain and range, but can you see or kind of think through the places where domain and range change? Like D, for example. For the square root function, what's the domain? 0 to infinity. If I take that and shift it to the left 2, what's the domain now? -2 to infinity. That moves along with it, right? Think about it like, like the graph is living in like a window or something, right? Its domain is 0 to the right. Well, you take the whole thing, you move the graph over, but that like window that it lives in, that moves with it as well. 0 was the smallest value that would work, but we slid the whole thing to the left. Now it's -2. It doesn't change the way it behaves, but it sort of slides the whole thing along with it. Okay. Okay, cool. So two things, vertical shifts and horizontal shifts, right? Vertical up and down, horizontal left and right. One of them probably feels a little more natural than the other, right? And one or two people asked me about this. When you shift vertically, how does that work? You add or subtract something, like here we subtracted 5, and what happened to the graph? It moved down, right? Down's the negative direction, right? That feels right, that tracks, that feels like it makes sense. here. We subtracted 5, but the graph shifted to the right. That feels backwards, right? Okay. And that's fine, it does, like, it feels backwards to me too. Horizontal shifts work that way, this is correct. When we group things in like that, one way of looking at it is, we're kind of on opposite sides of the equal sign. So if I took like, y equals x and like whatever else is going on, this +5 thing, if I'm adding something here, it's like I'm changing the x value. If I added something over here, it's like I'm changing the y value, kind of, right? If you think about them that way and you group them on opposite sides of the equal sign, then they work the same way. The problem is, or not problem, but the thing that happens, the thing that causes one of these to feel backwards is that our default thing is to write a function as y equals with y all by itself on one side of the equation, right? Well, okay, that means that other stuff is on the other side of the equation from it. How do you move stuff from one side to the other? Do the opposite thing, right? If it was plus, you subtract. If it was subtraction, you add. So because of that, it makes one of them kind of feel backwards of the other. That's really what's going on. If you want a way to kind of think through it or, kind of help remember what's going on, it's often useful to think of the x value, the input, as being like when things happen. And a lot of questions, that's how we answer it. Like, when is this true? When or where are the x-intercepts? The way you answer is with the x value. Some of that. If I'm thinking about x as when something happens, then this -5, if I'm taking away from, when something happens, I'm sort of moving it later, right? Well, it pushes the whole thing to the right. If I add to it instead, I'm moving the timeline up, and that moves up. Okay, so vertical and horizontal shifts, you add or subtract either directly to the variable, so on the inside or before the function does its thing, or on the outside or after the function does its thing. And that affects things by either moving the graph horizontally, if it's on the inside, or vertically if it's on the outside, okay? So this inside and outside idea, we're gonna, come back to a lot. Stuff changing inside having an affect effect thing in my brain right now. I think that's right. Stuff changing inside affects the horizontal. Stuff changing outside affects the vertical. For effects? I don't know. It's not English class. Okay. All right. And for the moment, all we're doing is adding or subtracting. Adding or subtracting is always going to result in some kind of shift. It just, picks the whole thing up and moves it. Now, if you go back and look at all of these like parent function types that we've talked about, they've all got kind of distinct visual things that you can keep track of, right? For x squared, the point at the vertex, the bottom of the thing. For the absolute value, the corner, which is also called the vertex. Square root, at that point where it starts. Cubic or the cube root, got the point where it, on the flexion point, but this point where the curvature sort of changes over, right? It's a little bit harder to keep track of. It's not quite as distinct, but they've all got a point you can keep track of. Everything moves, but in particular that part moves. So if I'm trying to draw it, I can use that to kind of track what's going on. Okay. These other 4 examples then, we're combining these things and maybe doing 2 of them at the same time. So example 2, consider this function quantity x minus 1 all squared plus 3. Again, what's the parent function? How's it been changed? What does that do to the graph? Didn't ask you for domain and range, but maybe think through domain and range as you do that. 3, pretty much the same idea. 4, now we're going from a graph. One way that that's different is that if I start with the symbolic version of the thing. Your first step can be punch it into a calculator and look at the graph and try to describe what happens, right? If I give you the graph instead, I can't just start by punching that into a calculator. So I have to think through a little more, a little differently what's going on here. I need to recognize from the shape of the thing what kind of function it is, and then try to, figure out what the moves are and how that affects them. And then here, kind of described in words. So, again, we got 10 minutes or so. Let's spend that time kind of working on these. Y'all talk to each other, ask questions as they come up. Really what we need, parentheses are there. That thing that happened. I think we're where we're talking about. I get finished. So you want to square. So that the minus two, what you're saying is like you want that. Like, that's how you make it happen. No, so it's the. After the. Yeah, so when you like work a problem and have you do. That you proving to it. Satisfies that, right, then it's. Yeah, there was some. Yeah. Yeah, the first one was,
Just like that.
right,
Got it.
yeah. so the absolute value.
I went to go find security and knock on something. It used to be the quad. That information.
I don't have it yet.
Okay.
Yeah, I think everything is supposed to get started this week, but I haven't gotten like a schedule or anything.
We don't have a test for like,
It's 2 weeks from Friday, so yeah. 20th is our first.
saying they could return?
I think they're supposed to, I think they're supposed to be opening today, but I haven't gotten like a schedule or anything. So, you know, normally they send us like, we're open, you know, these times, but everything is kind of switched and working differently this semester. And I haven't gotten it. So, yeah. As soon as I find out something, I'll let you guys know, but I don't know anything yet. I would say, you know, if you have time or whatever, just drop by and you know, see what's going on over there on the library, but I don't know details yet. Okay, so let's just compare notes real quick. So number 2, consider this function. What's the parent function? Squared, okay. And how has it been changed? Right 1 and up 3. Does everybody agree? Okay, so the point at the vertex that used to be 0, 0 is now 1, 3. Right, if we go right 1 and up 3. Okay, 3, what kind of function we're talking about? Square root. Shifted. Left 3 and it says sketch it here. So give me 1 point on the graph of that. 0, 0. If we move left 3 and down 2 ends up at -3, -2. And then something along those lines, right? Anytime I say sketch something, I'm not trying to be like real precise there. Obviously, I'm just drawing a tiny one, but it looks something like that. Okay, 4. We gotta identify what kind of thing it is. X squared by the shape, right? Okay, so it's a square function, which means it came from a thing that looked like that. So how has it been changed, moved, shifted? To the right 2 and down 3. This point at 2, -3, that's kind of the key to the whole thing. So if we want to write down that function, what's it look like? x plus 2 minus 3 on the outside. And then once I have, it should be minus 2. You're right. Thank you. I told you. Told you it goes backwards to me sometimes too. Once we have, but here's the thing, once we have a thing that we think is gonna work, even if we couldn't start by graphing it, once I have a thing that I think does it, I can go graph it. And I graph it, look at it, and I go, oh yeah, the left-right thing, right? And that's easy enough to fix. Yeah? Okay. All right, and the last one, same shape as the absolute value, but shifted up 2 and to the left 6. So absolute value, left 6, and up 2. And then again, once I have a thing that I think works, I go graph it, I check to see if it actually does. If it doesn't, hopefully I'm close enough that I can figure out, how to correct and adjust. Okay? Pretty feel good about all that? Okay. So that's, about the halfway point for this transformation stuff. Next time we'll talk about reflecting and stretching, but that's shifting. This is the. I'll get the answer.
Above the campus store.
Yes. Yep. Thank you, you too.